Okay, so to continue with this, so the end point is when our pKa is equal to the pH. So to solve for our Ka value, so we already got the pKa. To solve for the Ka value, right, we do 10 to the negative pKa, 10 to the negative 3.75, which gives us a value of 10 to the negative 3.75. So 1 point, let me see for sig figs. 1. 1 sig fig, that's kind of crappy. So it's 1.778, but we're going to round that to 2 times 10 to the negative 4. Okay. And then for the second part of this, where it says determine the color. So if we determine if we get the pH value from this color, from this concentration, because this is a strong acid, which is helpful here, of course, because it's a strong acid, that concentration basically is your hydronium. So if you do negative log of the 1.8 times 10 to the negative 4, negative log 1.8 times 10 to the negative 4, we get 3.74. So in this question here, I guess technically in this part we're using only that value, but we still need to refer to it. No, I'm not too picky on this. This is a weird one because you have to use certain parts to answer certain things. Let's follow through and do just the 1. So this would be a pH approximately of 4. It's 3.74 to be specific. So because it's within, what color is this? Because it's within this range, it should be green, right? Okay, so let's look at the next one. So it says estimate the hydronium concentration in a solution given the following data. So for this one here, we're looking at, they've used 2 indicators on the same solution. So if you look at your table, phenol red is red when it is a pH higher than 8. So this indicates to us that we have a pH higher than 8. Like it's past the transition point for phenol red, right? For phenolphthalein, it says that it is colorless, which means it has to be a pH lower than 8.2, because 8.2 and lower is where it's colorless. So actually, when we're looking at this, I would say it's approximately, so we're estimating this, would be in between that, right? So 8.1. So if we want the hydronium concentration, and that's our pH, right? We do 10 to the negative 8.1. There's no numbers here to work with, so we're not worried about sig figs. Times 10 to the negative 9 moles per liter. Okay, so like using 2 indicators on the same solution actually gives us a lot of knowledge, right, about the range that it can be in. Okay, so next we have a few drops of alizarin yellow are added to this solution. So we have a base solution. What color should the indicator display? Explain your answer by showing the work, because we've got to do our calculations here. So alizarin yellow, let's just write this down. 10.1 to 12.0. So this is yellow to red. So in between that is going to be an orange color, right? Okay, so we've got a strong base. So that means our hydroxide concentration is equivalent to that. So we can get our POH by doing negative log. Right? Negative log 0.001 is 3. So the pH of this solution then is 14 minus 3, which is 11. So actually, it's in between that, so it should be an orangey color. Okay, number 4. This is similar to the other one where we did where it had a bunch of information showing you color changes, right? So it says, like thymoblue, the indicator alizarin undergoes a different color change over 2 pH ranges. So what that means is there are 2 Ka values because we have 2 different transition points. Okay, so what this means actually is that alizarin must have 2 hydrogens that it's able to give away, right? So it would be a diprotic weak acid. So the first transition is going to be essentially the loss of the first one. Of course, this is with water, right? I'm not showing the full thing here, but hopefully you understand what I'm saying. The second, so this would be our Ka1. The second one would be the next equilibrium where it's losing the second hydrogen, Ka2, right? So that means that you're going to have a pKa1 and a pKa2. So what does it want us to do? The K values. Okay, so the first transition is here. The second transition is here. So we need to find the difference between these two values and get the average. Right, so 5.6 plus 7.3 divided by 2 is 6.45. So pKa1 is 6.45, right? And then we would do the same thing here. So the difference between 11 and 12.4, 11 plus 12.4 divided by 2 is our pKa2, which is 11.7. Okay, so to get the Ka values, of course, we're going to do 10 to the negative. So I'll use a different color here. So Ka1 is going to be 10 to the negative pKa1, right? Which is 10 to the negative 6.45, which is, again, we don't really have numbers here, so I'm not really concerned. 3.55 times 10 to the negative 7. And then here we're going to do Ka2 is 10 to the negative pKa2, which is 10 to the negative, what did we say, 11.7, which is 10 to the negative 1.995. Times 10 to the negative 12. Yeah, I wouldn't worry about sig figs here. Okay, so those are our 2 values. All right, so if it's something that had 3 transitions, that means they would have had 3 hydrogens, like 3 different hydrogen equilibrium. This is like when we do, carbonic acid, right? It can become HCO3 and then CO3. Same idea. Okay, so I'm going to suggest that you pause the video here and give this one a try. This is a really interesting question. I'll put a little star beside this. So it says, the following 0.10 mole per liter salt solutions have their labels removed. So you're dealing with the salts now. So we have sodium bisulfate, sodium carbonate, sodium dihydrogen phosphate, and here we have ammonium, and this is, what is this guy? Methanoate. Okay, so it says the solutions are tested with 3 indicators and shown the following results. So we have 3 different indicators and we have the color. So this is actually combining what we learned in chapter, I should say the same chapter, but 6.1, where we looked at the different salts and how those are acidic or basic, and narrowing it down here to what pH we would expect. Okay, so pause the video here, give this a try, and then come back to see the full answer. Okay, so let's break this down. So we know all of these are group 1. We're not really concerned with it. So we have HSO4, we have carbonate, we have H2PO4 -1, and we have NH4 NH4 is a little bit of a different beast. NH4, CH3, COO. Okay. So HSO4 can be, is technically amphiprotic, but remember that when it becomes H2, if this were to act like a base, H2SO4 is strong. So that's actually not going to form properly. So this will behave like an acid. So the Ka value from our chart, 1.2 times 10 to the negative 2. Carbonate can only behave like a base. So this is an acid. This can only behave like a base. So we can just write down now that it's going to be a base for now. Okay, we may have to compare that. Anyway, H2PO4 can act like both an acid or a base. So you would have to look up the Ka value and determine the Kb value for this. So the Ka value here, H2PO4, where am I looking? Where's H2PO4? H2PO4 is 6.2 times 10 to the negative 8. And as a base, we need the conjugate of H3PO4. One times 10 to the negative 14. I'm not even sure if we really need to do this calculation, but I'd rather just have it done if we need it. Okay, so Kb is 1.33 times 10 to the negative 12. So this is also behaving like an acid. And then here we have two things happening. We have an acid and we have a base. So this guy here, the Ka value is 5.6 times 10 to the negative 10. The Kb for this, we would have to compare the K. So again, we're doing Kw over Ka. This has to be for the acid form of that. CH3, where am I looking? Which is, so we do 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. So this guy is 5.56 times 10 to the negative 10. So actually this is pretty close to being neutral, right? So like those numbers are very, very close to each other. So I would say this is pretty much neutral, which is probably going to help us with determining what's going on up here. Okay, so this is just a rough estimate. So we should have two acids, we should have a base, and we should have something that's neutral. Pardon me. I know you guys know that I'm sick. Okay, so let's look at our ranges. This is like deciphering like a puzzle, like, I don't know, an escape game, a chemistry escape game. Okay, so let's look at bromothiamyl blue. So bromothiamyl blue, we know, is when it's, okay, so when it's blue, that means it has to be a pH higher than 7.6, right? Methyl orange, if we look at the range, if it's yellow, that means it has to be higher than 4.4. And phenolphthalein, if it's pink, means it has to be higher than 10. Okay, so solution A is something that has a pH higher than 10. For sure, for sure. Okay. Solution B is green for bromothiamyl blue. So actually that's going to be approximately 7 because it's in between 6 and 7.6. So I'm going to say right here, solution B is going to be our neutral solution, right? Which is going to be our NH4CH3COO. And we'll continue this in the next part.